Welcome to this explainer. Today, we're pulling back the curtain on the invisible machinery of the internet that we take for granted every single day. We're talking about the TCP IP protocol revolution, basically the unsung hero of our digital age. Okay, let's dive into this and explore how a handful of stubborn engineers completely reshaped human communication.
I mean, think about it for a second. What actually happens behind the screen when you tap send? A message crosses the entire planet in less than a second. A high-definition video streams from a server thousands of miles away as if it were sitting right next to you on the couch. It happens so flawlessly that we rarely pause to ask how this enormous system was built or what rules govern the billions of devices silently talking to each other in the dark. It's nothing short of modern magic, but it required decades of serious problem-solving to achieve.
Section 1, the invisible network, tracing the origins. To really understand how this works, we've got to go all the way back to the beginning, setting our scene in the late 1950s.
Picture this. It's an era of incredibly high global anxiety. In 1957, the United States watched the Soviet Union successfully launch Sputnik, the very first satellite in orbit. The steady beep of that satellite passing overhead sparked a massive wave of fear about falling behind in technology. So the direct response from the U.S. government was creating a research agency called ARPA, the Advanced Research Projects Agency. Their sole mandate was to fund bold, forward-looking projects that might otherwise never get off the ground, just ensuring they'd never be technologically surprised on the global stage again.
Section 2, packet switching, a data breakthrough. By the 1960s, ARPA researchers hit a major roadblock, pushing them toward an incredible breakthrough in data transmission.
And this brilliantly illustrates the problem. Back then, computers were massive, incredibly expensive, and completely isolated. If you weren't physically standing in the building, you just couldn't use the machine. Researchers desperately needed to share computing resources, but the dominant communication technology, the telephone network, was terrible for computers. See, telephones use something called circuit switching, where a single continuous connection is reserved just for your call. That's great for human voices, but highly inefficient for computers that send data in short, explosive bursts. Enter researchers Baran and Donald Davies. They proposed a radical alternative. Instead of a single reserved path, what if you broke information into small chunks, sent them separately, and let the network figure out the best route? Davies famously called this packet switching.
That brilliant idea became the foundation for a project called ARPANET in 1969. And the very first message ever sent on this network is notoriously unglamorous. On October 29th, researchers at UCLA tried to send a message to a computer at Stanford hundreds of miles away. They attempted to type the word login. They typed the L, then they typed the O, and then the entire system crashed. Just 2 letters. Well, they eventually fixed the connection and sent the full message, but that anticlimactic LO was literal history in the making. It was the very first time 2 separate computers exchanged information over a long-distance network built specifically for that purpose.
ARPANET grew steadily from 4 computers to dozens over the next several years. But as time marched on, a massive new fragmentation problem was quietly emerging. Different networks were being built independently all around the world by different academic and military institutions. There were satellite networks, radio networks, and terrestrial networks. And here's the kicker. They were all using completely different technical standards to operate.
Section 3, the TCP IP revolution, bridging networks. Which brings us to the real climax of our explainer, the true birth of the interconnected world we know today.
This fragmentation was a huge point of tension for engineers. You had all these fantastic, growing networks, but none of them could communicate with each other. So the crucial point is, how do isolated networks actually talk to each other? It was exactly like having several countries speaking completely different languages, with absolutely no translator between them. If you were on one network, you were completely isolated from the rest. The dream of a global system was just stalling out.
The elegant solution to this chaos came from 2 visionary researchers in the 1970s, Vint Cerf and Kahn. They designed a universal set of rules, or a protocol, allowing computers on completely different networks to reliably communicate, regardless of the hardware or software they used. They called it TCP/IP. It acted as the ultimate universal translator. TCP, or Transmission Control Protocol, makes sure that data arrives completely and in the correct order. IP, the Internet Protocol, handles the addressing, making sure every single piece of data knows exactly where it needs to go on the map.
Implementing this wasn't just a gradual shift. Actually, scratch that. It wasn't gradual at all. It was a hard transition known as Flag Day. On January 1st to 1983,
Every single computer connected to ARPANET was required to switch over to TCP/IP. This mandated switchover is a legendary date in tech history. It's widely marked as the official birth of the modern Internet. It is the exact moment that separate, fundamentally incompatible networks finally merged into one unified, globally comprehensible system.
Now, while TCP/IP built this incredibly robust foundation, the Internet was still mostly a dense, text-based tool for governments and universities. It definitely wasn't user-friendly. But that all changed in 1989 when a British scientist named Tim Berners-Lee, working at CERN, proposed a new system. By using clickable text links to visually organize information, he created the World Wide Web. By the mid-1990s, thanks to user-friendly web browsers running directly on top of that TCP/IP foundation, the Internet absolutely exploded into homes, schools, and businesses worldwide.
Section 4. How Data Travels, the Modern Request. Let's bring this right back to the present day and apply these historical rules to the data traveling to your device right now.
Every single time you load a page, send a text, or stream a video, a highly orchestrated sequence occurs in a fraction of a second. Let's move to and see how this builds, walking through the anatomy of a modern request. First, your data is broken into those packets we talked about earlier. Second, it finds the destination IP address via DNS. Third, those packets are routed individually through the global network. And fourth, they're reassembled perfectly at the destination using TCP. Decades-old rules governing every single click today.
To clarify that second step, because let's be real, nobody actually types out long numerical IP addresses to visit a website, we use human-friendly names. That's where the domain name system, or DNS, steps in. It works exactly like a phone book for the Internet. When you type a name, a DNS server looks up the matching numerical IP address and sends it back to your device, giving your packets the exact mathematical coordinates they need to start their journey across the globe.
Now, what's really interesting here is the extreme flexibility of it all. Remember packet switching? A single packet might hop through a dozen or more specialized routers across cities or even continents. Because the data is broken into independent chunks, it doesn't rely on one fragile continuous connection. These specialized routers look at each incoming packet and independently decide the best next path. Packets from the exact same message can take completely different routes to flexibly bypass network congestion or damaged fiber optic cables, arriving at the destination from many directions at once.
And finally, your device reassembles all of those arriving packets in the correct order, guided by the strict instructions carried by TCP. If a packet goes missing along the way, TCP simply requests it again. This entire massive global operation, breaking data down, routing it across continents, translating names, and putting it all perfectly back together, happens so fast we never even notice it. It's a quiet kind of genius hidden completely behind a blinking cursor and a loading screen, relying on the exact same simple principles laid out by those engineers decades ago.
What began as a small Cold War research project connecting 4 isolated computers has grown into a vast, sprawling global network linking billions of devices. So I leave you with this. The next time a web page loads instantly or a video starts playing without a single hitch, will you take a second to appreciate the invisible, globe-spanning journey of your data? Thanks for joining me on this explainer, and keep staying curious about the hidden systems that seamlessly power our world.